Hey guys, welcome back to spectroscopy. We are entering into nuclear magnetic resonance spectroscopy today. We focused on infrared spectroscopy last time. Nuclear magnetic resonance spectroscopy, or NMR, gives us a lot of information about specific parts of our molecule and helps us start to put a molecule together, not just identify its functional groups. Remember from Gen Chem that every nuclei has an allowed number of spin states based on their spin quantum number L. For hydrogen, for example, L is 1/2, which means you have two allowed spin states, spin up or spin down. Carbon-13 is exactly the same way. It has an L of 1/2, which means it can be spin up or spin down. Now, one of the interesting things about nuclei spins is that they are random. So they are kind of just all over the place. They can be in any orientation. When you apply a magnetic field, B naught, to that amount of nuclei, what happens is that they align with the magnetic field. So if my magnetic field is going up, they align up with my magnetic field. This is considered the low energy state. They are aligned with the applied field. And what happens is that you can irradiate these nuclei with a radio frequency. Think back to your electromagnetic spectrum from last time. What happens is that these nuclei absorb the energy and do a spin flip. They flip so that now they are aligned against the applied field. The difference in energy between these two nuclear spin states for a given nucleus is proportional to the strength of the magnetic field experienced by the nucleus itself. There are several different types of nuclear magnetic resonance spectroscopy. The two that are most useful to us in organic are hydrogen and carbon spectroscopy. Every NMR spectra has a reference peak. So you're going to see in just a second an example of a NMR spectra. On the x-axis is something called chemical shift. This is a shift in parts per million from a reference signal. The reference signal is set at 0, and the reference is TMS, or trimethylsilane. NMR works by placing your sample in an applied magnetic field. Your sample is typically dissolved in CCl4, CdCl3, or D2O. The reason for this is because you don't want any hydrogen atoms that can interact with your sample or adjust your field in any way. Once you apply a magnetic field to your sample, this forces the nuclei to align with the magnetic field in the lower energy state. A radio frequency then irradiates the sample, and the nuclei absorb the energy and flip to the higher energy spin state. Resonance is the absorption of electromagnetic radiation by a precessing or a spinning nucleus and the resulting flip of its nuclear spin from a low energy to a high energy state. The spectrometer detects the absorption and records it as a signal. So here's an example of methyl acetates. You've got your TMS peak down here at 0, and this spectrum has two signals, one at about 2 and one at about 3.5. Now, obviously, we're looking at a proton spectrum here, and there are 6 hydrogens in this molecule, but they are not what we would call equivalent. And we'll talk about equivalence here in a second, but you will not always get 6 signals if you have 6 protons. In fact, it is very unlikely that you will get 6 signals for 6 protons. A key physical principle for NMR is that circulating electrons induce a magnetic field. The converse is also true. An applied magnetic field induces electrons to circulate, and the orientation of the field dictates the direction of circulation. The circulation of electron density in a molecule in an applied magnetic field is called diamagnetic current. A molecule's sigma bonding electron density is induced to circulate opposite the magnetic field. As a result, the circulating electrons experience a magnetic field that is slightly smaller than the magnetic field applied. In essence, they are shielded. The degree of shielding depends on several factors that we will look at later. A nucleus that is more shielded more shielding around the nucleus, will come into resonance at a lower frequency, lower chemical shift, than something that is less shielded. We refer to this in NMR as downfield and upfield. So something closer to your TMS peak is more shielded and is considered upfield. Something that is less shielded is considered downfield and is further to the left. Now let's talk about those equivalent hydrogens. So you can see here in this chloropropane molecule here that we've got 7 different hydrogens. We've got 3 on each methyl and 1 by itself. Those 2 methyl groups are on either side of a plane of symmetry. Those 2 methyl groups are what we would call equivalent. The reason is that they are in the same environment on both sides of that carbon in the center. You can look at several different examples of this. So let's take 2-methylpropane. We've got 3 carbons that each have 3 hydrogens. And we've got 1 hydrogen in the middle. The 3 methyl groups, in this case, all 9 of those hydrogens are in the same environment. They're all bonded to a carbon, which is bonded to that central carbon. That central carbon is bonded to that hydrogen. I would get 2 signals from this molecule. I would get a signal for 9 hydrogens and a signal for 1 hydrogen. We can look at other molecules as well. 2-methylbutane, for example. I have 3 hydrogens here, 3 hydrogens here, 3 hydrogens here. But those methyl groups are not all equivalent. 2 of them are because they are both attached to another carbon that has a hydrogen. So I would get 1 signal for those 2 methyl groups. I would get another signal for this methyl group because it's in a different environment. I would get another signal for these 2 hydrogens and another for this hydrogen. So I would get 4 signals for this molecule. I would get a 6 hydrogen signal, that's my 2 methyl groups, a 1 hydrogen signal, a 2 hydrogen signal, and a 3 hydrogen signal. Typically, you can see that symmetry in a molecule results in equivalent hydrogens. So for example, for propanone, 3 hydrogens on either side of that double bond oxygen, they are equivalent. You will get 1 signal for that molecule on your NMR spectra. Same thing down here. Let's look at cyclopentanone. So this carbon here has no hydrogens on it. This one has 2, 2, 2, and 2. The 2 that are right next to your oxygen are going to give you 1 signal, and these 2 are going to give you a second signal. You would get 2 signals for 4 hydrogens each in this molecule. Now, one of the questions you're probably going to ask yourself at some point when you're working on these is, how do I know how many hydrogens are responsible for each signal? Well, believe it or not, we have a way of understanding this based on integration. So modern NMR spectrometers automatically integrate things for you. The best way to look at this, though, is by height. So for example, there's the height of my signal at 2. Here's the height of my signal at about 1.5. I have 9 equivalent hydrogens on my molecule, and then another 3 over here. The tallest signal and the shortest signal, in this case, I've only got 2. My tall signal is responsible for 9 hydrogens, and my lower signal is responsible for 3. And if you actually look at this, the 9 hydrogen signal is twice as high as the 3 hydrogen signal. So you can actually tell how many hydrogens are responsible for each signal based on the height of the signal itself. The chemical shift of a hydrogen can also give us valuable information about the types of hydrogens that give rise to the signal. So for example, a hydrogen that's part of an aldehyde is going to show up much further to the left than an alkyl group, for example. This is very similar to what you saw in IR, that there are representative spots where particular hydrogens are going to show up in our chemical shift diagram here. Shielding depends on three factors. We talked a little bit about this earlier. The first is the electronegativity of nearby atoms. If something has a very large electronegativity, it's going to have a greater chemical shift. You can see that with halogens as well as oxygen. So fluorine, of course, being our most electronegative atom, and it's going to have a high chemical shift. And we're still looking at the signal for the hydrogen, so keep that in mind. Something like iodine, though, is going to be lower in chemical shift because it's less electronegative. Hybridization of adjacent atoms also matters. So something that is sp3 hybridized is going to show up very low in chemical shift, whereas something that is sp hybridized is going to show up much higher in chemical shift. The third thing that depends on shielding is magnetic induction within an adjacent pi bond. That's less important to us right now, but what it does tell us is that all 6 hydrogens of benzene, which looks like this, all 6 hydrogens of benzene are equivalent, and so you would get a singlet at about 7.5. A singlet, Dr. M, what are you talking about? Well, hydrogen NMR splits signals. You're going to work with this a little bit in class, but there's this n+1 rule that's actually very helpful when we're talking about the splitting of a signal. So a signal does not just show up as a line, for example. A signal can show up as something like a doublet, or a triplet, or a quartet, or any other multiplet like that. When a signal is split, we use the n+1 rule. The n+1 rule says that if a signal is split into a quartet, it is next to or vicinal to n+1 hydrogens. Okay, and we're looking at this kind of backwards. Something that is split into a quartet is next to 3 hydrogens. Something that is split into a triplet is next to 2 hydrogens. So the n+1 rule really says if you're next to 3 hydrogens, you're going to split into 3 + 1. You're going to split into 4 peaks. This is going to become very, very important because it helps you start to put together a molecule. So here's an example. Here's 1,1-dichloroethane. The first thing I would look at when I see this spectra is that I have a doublet, 1, 2, at about 2. So I know that this has to be vicinal to or next to 1 hydrogen. And this is a signal for hydrogens. This quartet, on the other hand, is a much lower signal. So that helps tell me how many hydrogens are responsible for this signal. But a quartet must be vicinal to 3 hydrogens. And that actually is the case. So if you look at this hydrogen right here, it is vicinal to 3, so vicinal being right next to. So it's vicinal to 3 hydrogens, which means it splits into a quartet. These 3 hydrogens, on the other hand, are vicinal to 1, so that's going to split into a doublet. Complex splitting patterns can arise when sets of hydrogen atoms are coupled to the nuclei of more than one set of other hydrogen atoms. You're going to see this as a multiplet most of the time, so it's going to look like that, for example, and that's a very messy signal, and multiplets are messy. We'll talk a little bit more about complex splitting patterns when we get into class, but for now, just know that complex splitting patterns do exist. You can also get coupling of hydrogen signals if they are on something like a double bond. These are considered geminal hydrogens, and they cause even more different types of splitting than you've seen already. Carbon NMR spectroscopy is another very useful tool. And instead of talking about the types of hydrogens in a molecule, we're talking about the types of carbons in a molecule. Carbon spectra do not split, and there's a reason for this, but carbon spectra are going to show up just as simple lines. If you have 4 lines in a carbon spectra, for example, you have 4 different types of carbon in your molecule. Here's an example of 1-bromobutane. Again, here's our TMS peak. And then I have 1, 2, 3, 4 different types of carbons in this molecule. And because I only have 4 carbons, I know that each of my carbons must be a distinct carbon and they must be different from each other. Just like with proton NMR, carbons give particular chemical shifts. You'll notice in carbon NMR that we still have our TMS peak, but we go much higher in chemical shift now. That's one of the ways you can tell a difference between a proton NMR and a carbon NMR. So what in the world are we looking for in NMR? Well, there's a few things that you should do when you see an NMR spectra or when you're trying to put together a molecule. The first thing you should do is calculate the index of hydrogen deficiency. So the index of hydrogen deficiency says if I have 6 carbons, the normal alkane for that would be 6 times 2 plus 2. So it would be C6H14. So this is normal. And if my molecule that I were trying to put together was C6H12, simply subtract the 2, and my index of hydrogen deficiency is 1 H2 molecule. Okay, you're always going to look at this as H2 because that's hydrogen. Like hydrogen gas, for example, is H2. What this means is that I have 1 double bond or ring in my molecule, and that helps me put it together. Let me give you we'll do some more examples of this later. But when you're looking at a molecular formula, halogens count as carbons, oxygens you just don't count, okay? And you'll see why that is as you do them. Once you've figured out the index of hydrogen deficiency, you can tell whether something is in a ring, whether there's a double bond, whether there's a C double bond O, all that kind of stuff is told to you by the index of hydrogen deficiency. The last 4 things you want to look at are specific to different molecules. So I always start by looking at the number of signals. So if I have 6 carbons, for example, and I have 6 lines on my carbon NMR, that means all 6 of my carbons must be distinct from each other. Most of the time, you're going to find that there are equivalent hydrogens in your molecule because there are not, for example, with this one, 12 hydrogen signals. You then want to look at where the hydrogen and the carbon signals show up. So use those 2 charts that you saw earlier in these slides to see what chemical environment those carbons and hydrogens might be in. You then want to look at the intensity and the multiplicity of the signal for hydrogen NMR. Now I can stand here talking about this all day, but practice problems are probably more helpful. So let's do a few. Okay, so this molecule has a molecular formula of C5H10O. So let's do our index of hydrogen deficiency. A normal 5-carbon compound would have 12 hydrogens, and this one has 10. And remember that oxygen doesn't count. So I would have an index of hydrogen deficiency of 1. That means I have 1 double bond or ring in this molecule. I have 2 proton signals. This is my TMS peak, so I can ignore it. But I have 2 proton signals, which means my molecule has a lot of equivalent hydrogens, all right? So what do I know about these hydrogens? Well, I can tell from here and here, the height of my signals, that I've probably got maybe 3 hydrogens responsible for this one and 2 hydrogens responsible for this one. But 3 plus 2 does not equal 10. But wait, let me double it. If this is responsible for 6 hydrogens and this one's responsible for 4, now I equal 10. These are proportional to each other, okay? They're not always going to be 1s, 2s, and 3s. Sometimes they're going to be more per signal. So let's look at each of these signals. Okay, this is the one at chemical shift 1.07. It splits into a triplet, which means this signal's hydrogen is next to 2 other hydrogens. And those can be one on each side, both of them on the same side. We'll see how to put it together in a second. This one splits into a quartet. And that means that the signal that this is responsible for is next to 3 hydrogens. That to me indicates we probably have a couple of CH3 groups. Because if I have a couple of CH3 groups, well, that accounts for 6 hydrogens, right? And my 6 hydrogens have to be next to 2 other ones. So CH2, CH2. I only need 1 more carbon, and I still need an oxygen. Well, hey, that might work. Part of the problem with NMR that a lot of students encounter is that it's kind of like a puzzle, but sometimes you don't feel like you have all the pieces. I promise you, if you keep working at it, you will find all the pieces. One of the things that I think is very helpful to do is to assign which signal is responsible for these hydrogens. So for example, the CH3 group here is a triplet. It is next to 2 hydrogens. So this would be what I would call signal A. The CH2 is next to 3 hydrogens. So that would be signal B. And then the same thing is true on the opposite side of this carbonyl group. Let's take a look at another one. So this is C7H14O. So let's do index of hydrogen deficiency. So C7 normally would be H16, and this one is H14. Remember, O doesn't count. I have 1 H2 deficiency. I have a signal that is responsible for 9 hydrogens, 3 hydrogens, and 2 hydrogens. And interestingly, these are all singlets. That means that none of them are next to any other hydrogens. There are no vicinal hydrogens. Now, how in the world do we make that work? Well, let's start trying and putting some stuff together. So if I put together 7 carbons in a line, 1, 2, 3, 4, 5, 6, 7, these 3 hydrogens would be vicinal to 2, and I already can't make this work, right? So let's try something different. Let's try putting like a tert-butyl group together. 1, 2, 3, 4, 5, 6, 7 carbons. 7. These 3 hydrogens here on each of these methyl groups are vicinal to 0 hydrogens. That actually might work. And in fact, all 3 of those methyl groups amount to these 9 hydrogens right here. Now I just have to put together 3 hydrogens and 2 hydrogens that are vicinal to nothing else, and I still need an oxygen and a double bond somewhere. Well, believe it or not, this is going to be my CH3 group. So I'm going to label these as signal A, B, and C again. So signal A are my 3 over here. Signal B could be those 3 hydrogens, but they can't be vicinal to any other hydrogens. So let's put our double bond O right there. That leaves me with two hydrogens that could be responsible for signal C, and they are vicinal to no other hydrogens. Can you start to see how putting a molecule together can be kind of fun? You just have to have all the pieces, and I promise this gives it to you. The last thing I want to talk about today is two-dimensional NMR. So two-dimensional NMR takes advantage of several different components. So I want to first look at the proton NMR of this structure. So we have C7H14, which would normally be H16. So we're calculating our index of hydrogen deficiency. So I have one double bond or ring somewhere in this molecule. This first one here is my TMS peak, so I don't really even need to look at that. And then I'm going to label these as A, B, C, D, and E. Signal A is about half as tall as signal B. Signal E, C, and D are also much shorter. I need to account for 14 hydrogens somewhere in here, and we'll see how to do that here momentarily. All right. Signal A is a triplet, which means this signal is vicinal to 2. Signal B is a doublet, which means it is vicinal to 1 hydrogen. Signal C is a 1, 2, 3, 4, 5, 6. This is a sextet, which means it's vicinal to 5 hydrogens. D is a triplet, which means it is vicinal to 2. And E is a 1, 2, 3, 4, 5, 6, 7 septet, which means it is vicinal to 6 hydrogens. Okay. Before I do anything else to this, I want to show you what the two-dimensional NMR looks like. And I'm going to keep this A, B, C, D, and E when I look at this two-dimensional NMR. Two-dimensional NMR in this case is proton versus proton. The thing that this helps us with is determining which signals are next to which other signals. So the first thing you want to do with two-dimensional NMR is draw a line right through the middle, diagonal right up the top. Signal A in my previous slide, if I go back up here, at 0 is my TMS peak, and signal A was at about 0.9. So up here is my TMS peak, and at about 0.9 was signal A. Means this is signal B, C, D, and E. I'm going to go back to the last slide to get some more information here in a minute, but this is what a two-dimensional NMR helps you with. Look at C for me. If you go straight up and straight over, that meets letter A. That means whichever hydrogens are responsible for signal A are right next to signal C. D is going to be right next to C. And E is going to be next to B. So C is going to be in the middle of D and A. And then E and B are going to be next to each other. Okay? That's very helpful, actually. So I'm going to take this to our last slide, DCA and then EB. So I know that DC and A are right next to each other, and then B and E are going to be right next to each other. Now I just have to start putting this together. Well, one of the things that's very helpful to me is figuring out how many hydrogens are responsible for each of these signals before I start trying to put something together. So I'm going to start by assuming that this is a 6 hydrogen signal. That means that my triplet is likely going to be responsible for 3 because that's about half the size. This triplet over here is pretty close to 3. and then maybe a 1 hydrogen and a 1 hydrogen signal. Let's see if that adds up to 14. 6, 7, 8, 9, 10, 11, 12, 13. So one of these is a little bit off, but that's okay. I can work with that for the time being. My guess is that sextet is going to be responsible for 2 hydrogens because it is a little bit taller than the 1 hydrogen signal for E. So let's start putting a molecule together. Well, I know that the signal for D has to be responsible for 2 hydrogens and next to 2 hydrogens. So that's likely a CH2 group. And it's next to 2 hydrogens, which is likely another CH2 group. And that's going to be the signal for C. And C is next to A, which is responsible for 3 hydrogens. So that takes care of close to half of my molecule. I know that B is responsible for 6 hydrogens. So just for kicks, let me put a signal for E here and a signal for B here. These have to be CH3 groups, and they have to be next to 1 hydrogen. Well, that would make sense so far. That would mean my signal for E has to be responsible for 1 hydrogen and is next to 6. So it would be vicinal to 1, 2, 3, 4, 5, 6. So far, so good. My signal for D is responsible for 2 hydrogens and is next to 2. My signal for C, that's the one that I needed to check, was responsible for 2 hydrogens rather than 1. And now I just need my double bond because I have an index of hydrogen deficiency of 1 and an oxygen. Without that 2-dimensional NMR, it would have been a lot harder to figure out what signals went next to what. This 2-dimensional NMR helped us determine which signals were right next to each other in our final molecule. Now, before you go giving up on me, NMR is hard, but I promise you that I will help you work through it. It gives us so much information, and I hope that you are excited to start putting molecules together and start solving this puzzle.